Alright, it is time to talk about nuclear chemistry. So this is tricky because nuclear chemistry, those two words don't normally go hand in hand. Actually, most nuclear stuff is physics. And it's deceptive because when you look at nuclear, we're talking about protons, electrons, neutrons, lots of things that look like chemistry, but since it's an interaction of those particles, it's not really chemistry, it's more physics. So there's going to be a lot of times in here that you say, why, Mr. Jones, why is that so? And it's because of physics. And I'm not really going to get into the physics part because I don't want to overwhelm you with a lot of information that isn't necessary. As far as the AP test goes, the nuclear portion of it, it's very small and mostly just deals with half-life and decays. I'll try and slip in a couple cool facts here and there, but a lot of this stuff is just going to be on the scope of this class, so I'll try and keep it simple. Alright, first off, let's talk about the nucleus. So the nucleus is made up of protons and neutrons, with the neutrons being neutrally charged particles and the protons being positively charged particles. There's a problem here if you look at this. So check this out. Neutrons, they're neutrals. They're not going to affect each other. They're not going to affect the protons. But here we've got a proton, which is positive, and another proton, which is also positive. What do like forces do to each other? If you said repel, you're correct. So those two guys right there, they should be repelling each other. So what is it that holds the nucleus together? What is it that keeps it from just blowing apart if you got these positively charged particles being brought really close together like that? Why don't they just fly off the handle and go everywhere? This would be like bringing a bunch of North Pole magnets together and trying to cram them into one tight space. They would fall apart. So what's different about positively charged protons, what's different about the nucleus that causes this to hold together despite all odds? Truth is, it has nothing to do with odds. Instead, it has to do with electrostatic repulsion and the nuclear force. So the nuclear force is a term that you'll hear in physics. Okay, this is where it departs a little bit from the chemistry. So nuclear force is what holds them together, and it's a force that's actually a lot stronger than any other force in the world. It's so strong that it can hold positively charged protons together. And that binding energy, that nuclear force that holds them together, if you look at this kind of interaction model, that binding energy, all those red arrows, are strong enough to where they can hold it together and overcome that repulsive force. So here's the thing with the nuclear force. The nuclear force is kind of interesting because it repels at close range. So if you bring protons really close to each other, they'll repel each other, but it attracts at a slightly larger distance. So if they start to spread away from each other, it'll pull them back together, and so you get kind of this happy medium to where the protons are repelling each other at a distance, but they're attracting each other, and so they end up holding together. Let's stray a little bit from the chemistry and talk about some of the cool physics parts of this real quick. So protons and neutrons are made up of what's called quarks. Quarks are elementary particles or fundamental particles. So what that means is there is nothing smaller than a quark, because a quark isn't made of anything. Think of, for example, Legos. You know, from Legos you can build a car, you can make a tower, you make all kinds of things out of Legos, but the individual piece, so the tiny little Lego that makes up that car or that makes up that castle, that would be like a quark. So it's an individual piece, and you don't build Legos out of Legos. So those individual pieces of Legos that we're talking about, those aren't made out of other Legos. They're just a Lego. So a quark is just a quark. It's not made up of anything. And just like you can have different types of Legos, there's different types of quarks. There's up quarks, down quarks, bottom quarks, top quarks, strange quarks, and charm. The other type of fundamental particle would be the lepton. So lepton, just like a quark, it's not made up of anything. It's used to make other things. And an example of lepton would be our friend the electron. So electron is a type of lepton. But anyway, back to quarks and how they hold together protons. So if we've got two protons like this, each one of the protons is going to be made up of 3 quarks each. And quarks have what physicists call colors, and the colors are blue, red, and green. They don't actually have that color. We can't see them, so they don't really have color. But for whatever reason, those creative physicists decided to name them based upon colors. So those quarks are held together by a type of particle that is called a gluon. A gluon is like an energy transport that bounces between the quarks. And when it does that, because it's moving around them, transporting something, it actually holds those quarks together very, very tightly. And same thing's happening over here. So there's a gluon particle that's bouncing between these guys and holding them together really, really tightly as well. Not only are the quarks within each proton interacting with the other quarks, the quarks from between these two protons are interacting with each other with a particle called a pion. So the gluon holds together the particles within the particle, and the pion interacts the particles between the particles. So the quarks are held together within each other by gluons. The quarks are held together separately by pions. And because those quarks are held together separately, it drags together these protons. So what holds together two protons is the interaction between the quarks that's in each of the protons with a particle called a pion. And it doesn't really seem like much, but that force, that bouncing around of that pion, that holds together something that should otherwise totally repel each other. So that's what keeps together every single atom that makes up this entire universe. Your body is composed of atoms that should be repelling each other, but they don't. They don't because of those pions and gluons within the protons. But enough about that. Let's move back to the chemistry stuff. So the nucleus contains protons, which have a positively charged, and neutrons, which have no charge. And digressing just a little bit, those two things, which are both made of quarks, are called hadrons. Protons and neutrons are known as, in chemistry terms, nucleons. So a nucleon because they're found in the nucleus. So when we look at the atomic isotope, like that isotope notation, we've got our symbol, so in this case U, which is uranium. We have 238, that would be the atomic mass, and that means there's 238 nucleons in the nucleus. So 238 different particles within the nucleus. And this number on the bottom, that's the atomic number, and that tells us the number of protons. So if there is 92 protons, and there's 238 total nucleons, and nucleons are protons plus neutrons, that means there's 146 neutrons. So 146 neutrons, 92 protons, makes 238 nucleons. So that's all of that. If you want to learn a lot more about the nucleus and the physics behind it, go on to YouTube or Google and type in hadrons or quarks or strong force. You'll learn a lot of information that's really not necessary to this class. Let's boil down what you should know from this little lecture, from the little tirade that I gave. So protons are positively charged and neutrons are neutral. There's absolutely no reason why protons should be held together, but they are by a mysterious force called the nuclear force, and that overcomes the repulsion between protons. You need to know what isotopic notation is, so that's this little form of writing out molecules down here. You need to know that the top number is the atomic mass, the bottom number is the atomic number, and atomic mass minus atomic number gives you the number of neutrons.